This is part two of the chapter 45 lecture notes, and we didn't quite finish this page, so let's come back to it. Um, we talked about in the top part that organisms that reproduce early at a young age will likely produce more offspring, and organisms that reproduce late are taking a risk that they might die before they're able to reproduce. Semel parity should be, make sure that's a vocabulary term that you need to know, occurs when a species reproduces only once during its lifetime and then dies. And then iteroparity describes species that reproduce repeatedly during their lives. All right, the salmon mates once and dies, so that's simulparity. The antelope would be iteroparity. Primates, such as chimpanzees and humans would be included, um, would also be iteroparity. Um, okay, these are graphs of population growth. You may know a little bit about this. If the population growth is a J-shaped curve, that's called exponential growth. So you may have learned this in math. So if it's a J-shaped curve, it's exponential growth. And bacteria are a good example of populations that have exponential growth until they don't. Exponential growth, and then they reach a carrying capacity. So this part of the logistic growth curve is the exponential growth part. So this is exponential growth, but at a certain point in time, if it's logistic growth, there's going to be a maximum amount, a maximum population size that the habitat can support, and that is the carrying capacity. Now, humans are still in the exponential growth stage. Um, Other organisms have reached carrying capacity, and they just kind of fluctuate year after year, but they stay around that carrying capacity number. When resources are limited, this is when we see carrying capacities. This is when we see logistic growth. And so for right now, at this point in time, the resources for humans are not, they're limited, but not enough to cause us, to go into logistic growth instead of exponential. We're still growing exponentially. Okay, so population growth in yeast. It says yeast are grown in ideal conditions in a test tube. They show a classic S-shaped logistic growth curve. So in that test tube, they eventually reach a carrying capacity because the test tube can't hold but so many yeast. Seal populations show more of a fluctuation around the carrying capacity because changes happen, year after year. So you see, and this is how it is in nature more, because there's different changes in resources, limiting resources such as food, shelter, water. As those resources change, or even like changes in the number of predators, are, the number of predators is high, then the population is going to go down a little bit. But normally, once any population reaches carrying capacity, it'll fluctuate a little bit above or below each year. Now, here we have some math. Um, so we're going to look at some growth rate calculations, and I'll go ahead and warn you, I did go through these slides, and I'm going to have to add a few notes because they don't really explain everything. But the first calculation is the change in number of individuals over time. So that's going to be birth rate subtract death rate. And the way you would calculate it is the birth rate times the number of individuals, subtract the in the population, subtract the death rate times the number of individuals in the population. Or if you understand algebra, you know that you can do birth rate subtract death rate times the number, and then times that number by the number of individuals in the population. Um, and if you use that calculation, you can just go ahead and substitute R means B minus D, or birth rate minus death rate. If R turns out to be positive, a positive R means that the population is increasing. And if R is negative, then the population is in decline, it is decreasing. So because if it's negative, it means that the death rate is higher than the birth rate. Okay, another calculation that we can do is the logistic growth calculation. And that's going to use R max. And R max is the biotic potential of the species. So you have to know the biotic potential of the species. You have to know the number of individuals in the population. And I better write that. I don't see it on here anywhere. R max is the biotic potential. Okay. And so N is the number of individuals in the population, and K is the carrying capacity. So if you look at this formula, if your population is growing, then the number of individuals, let me think for a minute. If the number of individuals in the population is higher than the carrying capacity, then that's going to make that whole fraction negative. So that would show a negative or a declining growth. And if the number of individuals is less than the carrying capacity, then it will show an increasing growth, further growth. All right, so density, okay, so population regulation. How is the number of individuals in a population regulated by nature, I guess, or by any kind of factors? There are two factors that tend to regulate population sizes. There are density dependent factors, which include that in other words, these are factors that are stronger whenever the density of the population is higher. The larger the density, the more crowded the population. These factors will affect the population more. Predation, competition between members of the same species is intraspecific, and members of different species is interspecific. But competition in general for resources, accumulation of waste, and diseases. So that's a good example. Disease is a density dependent factor. If you think about it, areas that are crowded, like even with human disease, areas that are more crowded, disease will affect the population more than if the area is more spread out. So the denser a population is, the greater its mortality rate, or the greater the number of deaths. Now, there are density independent factors that affect a population equally, no matter if it's crowded or spread out. Weather, natural disasters. So if you have a flood that wipes out an entire population, I don't care if there were 5 individuals or 5 million individuals, they all get wiped out by that flood. Pollution is density independent. Chemical and physical conditions are density independent. So these are going to influence population no matter what the population density is. Now, K selected versus R selected species has to do with um, how long they live and the amount of parental care. So, an elephant is a K selected species, so is a human. Um, they live long lives, they mature late, and they provide long-term parental care to a very few number of offspring. So that's a lot of factors in there. Um, oak trees are also case selected. They do produce many offspring that, of course, do not receive parental care, but they're considered case selected because they live a long time and they mature late. Our selected species are like fish. They have a large number of small offspring. So fish lay lots of eggs, and very few of them survive. Um, Dandelions, jellyfish, regular fish are our selected species. They mature early. They do not live very long. And some fish do live longer than others, but they still have many offspring and don't give any parental care to those offspring. Finding Nemo is not true. What was his dad? Marlin. Anyway, the in Finding Nemo, the dad searches for Nemo and he tries to protect him and raise him and all that kind of stuff. That's just false. Fish don't do that. So, characteristics of a species, if they're case selected, is that they mature late, they live longer, they have increased parental care of their young, increased competition, fewer offspring, and larger offspring. And then the R selected, they mature early, they do not live as long, they do not have as much parental care, sometimes it's none, decreased competition, they have more offspring, and the offspring are smaller. So that's the difference between K selected and R selected. This is showing the human population growth curve, which we've already said is exponential. Um, and you've got the world versus different countries. Europe is more in a logistic curve, but all the other countries listed are still in exponential growth. This is time between billions of years, starting with year 1800. In 1800, there were 1 billion people. In 1930, 130 years later, there were 2 billion. Just 30 years later, there were 3 billion. This is how exponential growth works. 15 years later, there were 4 billion. And what is that? 12, 12 years later, there were 5 billion. Um, Another 12 years later, there were 6 billion. Another 13 years later, there were 7 billion. And keep going. And it is predicted that in 2028, we'll have 8 billion. In 2054, we'll have 9 billion people on the earth. Um, these diagrams are called age structure diagrams. And age structure diagrams usually compare males to females. So the males are purple and the females are red. Um, and this shows the first one, stage one, shows rapid growth. Stage two shows slow growth. Stage three shows stable. And stage four says question mark. The rapid growth diagram narrows to a point. So that what that indicates is the number of individuals decreases with age. So in other words, like with the human population in in America, um, the number of individuals gets less and less with age. So most people die at an older age. The slow growth model, the number of individuals increases steadily with age. So it's just a wider triangle. And then stable shows the number of individuals per age group decreases gradually, and